All right, team, let's do this. Welcome to your killer revision on isomerism, completely laser-focused for your JEE main prep. We're about to cut through all the noise and get right to the stuff you need to score those marks.
And look, I'm not just making that up. This is a direct promise from the source material for this whole explainer. What you're about to see is the most efficient, no-fluff breakdown designed for just one thing: getting the answers right and getting them right fast.
Okay, so what is isomerism really? At its heart, it's actually super simple. Imagine you have the same exact set of Lego bricks, that's your molecular formula, but you can build them into a bunch of different shapes. That's all it is. Same parts, different final product.
Now, this whole world of isomers, it basically splits into two main continents. On one side, you've got structural isomers. This is where the atoms are literally wired together differently. The whole blueprint changes. On the other side, stereoisomers. Here, the wiring diagram is exactly the same, but the way those atoms are arranged in 3D space is different.
So let's tackle that first type, structural isomers. The key word to remember here is connections. The fundamental way the atoms are linked together is what's changing. This slide right here is your ultimate cheat sheet. Think of it like this. Chain isomerism is just changing the carbon skeleton, maybe from a straight line to something with branches. Position is like moving a lamp in a room. Same lamp, different spot. Functional is a total identity swap, like an alcohol becoming an ether. Metamerism is just shuffling the neighbors around a central atom. And tautomerism? That's the really dynamic one, where two forms are constantly flipping back and forth. You know these five, you've got structural isomers down. Okay, so that was structural. Pretty straightforward, right? Now for the second category, and honestly, the one that's a bit more challenging, stereoisomers. Here, the connections are locked in. It's all about the 3D geometry.
This slide is your essential vocabulary list for surviving 3D chemistry. Geometrical isomers, that's your cis/trans and E/Z stuff. Optical isomerism is all about how molecules play with light, and it all starts with a chiral carbon, a carbon atom that's attached to four totally different groups. Now this is absolutely crucial. That chirality leads to enantiomers. The best way to think about them is like your hands. They're perfect mirror images, but you can't stack them perfectly on top of each other. Diastereomers? Well, they're like non-identical siblings. They're stereoisomers, but they are not mirror images of each other.
And this is a classic exam trap, the meso compound. Look at it. It has chiral centers, so your brain immediately wants to say it must be optically active. But nope, it's not. And why? Because it has an internal plane of symmetry. It's like there's a mirror inside the molecule itself, and that symmetry cancels out all the optical activity. It's a trick question in molecular form.
Okay, enough with the theory. Now for the best part. This is your exam cracker toolkit. This is how you're going to solve problems with serious speed and accuracy. These are the shortcuts you absolutely have to know.
Let's kick things off with this super common question. They give you some big complex molecule and ask for the maximum number of possible stereoisomers. You're not going to sit there and draw every single one, are you? No way.
You're going to use this. 2 to the power of n, where n is simply the number of chiral centers in that molecule. This is your secret weapon. Just count the chirocarbons, plug that number in for n, and bam, you've got your answer. It's that easy, as long as there's no internal symmetry to worry about.
Next trick. Assigning E and Z configuration. People get so bogged down in this, but you can seriously do it in 3 seconds flat. Let me show you.
It's a dead simple 3-step process. First, look at each carbon in the double bond and assign priority to its 2 groups. Higher atomic number gets higher priority. Step 2, find your 2 highest priority groups. Are they on the same side of the double bond or on opposite sides? And step 3, just remember this little trick. Z is for the same side. If they're on opposite sides, it's E. Done. Next question.
And just as important, you need to be able to spot a chiral carbon in an instant. You can't use that awesome 2 to the n formula if you can't find n in the first place, right? This should not take you more than a second.
Here are the rules of the game. They are so simple. Rule 1, a chiral carbon must have 4 different groups attached. That's the golden rule. So what does this mean? It means you can instantly rule out any CH2 group. It has 2 identical hydrogens. It also means you can ignore any carbon that's part of a double or triple bond, because it physically can't have 4 groups. Scan, apply these rules, and you'll find your chiral centers in no time. Here's another key point, especially for questions about stability.
As you can see from this chart, the trans or E isomer is almost always more stable. And the reason is simple. The big bulky groups are on opposite sides, so they have more personal space. This means less steric repulsion, which is just a fancy way of saying they aren't bumping into each other. Less bumping, less stress, more stable molecule.
All right, we've built up your offensive skills. Now we need to talk about defense. These are the common traps, the classic mistakes that students fall for every single year. Knowing these is just as important as knowing the formulas.
You need to burn these traps into your memory. Trap number 1. R and S is just a naming convention for the 3D layout. It tells you nothing about whether it rotates light left or right. That's something you have to measure. Trap 2. Tautomers are real, separate molecules in equilibrium. They are not just different drawings of the same molecule like resonance structures. Trap 3. We've hit this one already. Having chiral centers doesn't guarantee optical activity. Remember the meso compound. And trap 4. To have E/Z isomers, each carbon in the double bond needs 2 different groups. If even one of those carbons has 2 of the same thing attached, there's no geometrical isomerism. Game over.
So to wrap this all up, let's put it into action. Forget just memorizing rules. Look at a molecule like the one on your screen. You see this on your exam. Can you apply what we just covered? Can you immediately spot a plane of symmetry? And what does that tell you? Is it optically active or is it a meso compound? That right there, that kind of rapid analysis is what's going to win you points on exam day.